So my colleagues have left me with this really awkward situation of having to introduce myself because all the people who run the control seminar aren't here. So hi, I'm Shai. I'm a professor here in the department, associate professor. As you might guess from these labels down here, I do a few other things. I'm actually a biologist by training. My PhD is in biology. I did my undergrads and masters in Hebrew University in Israel in computer science, math, and physics. And then I spent about a decade working in industry in various signal processing things, and I'm actually still doing that. I'm CSO of a startup that is doing some electrocardiology signal processing. And some students in the department may have taken signal processing classes with me. But today I'm going to talk about something completely different and I'm really excited about. So there's going to be a shameless promotion of my recent paper section in this talk, because we got a paper out about this just 2 weeks ago in a very prestigious journal, Proceedings of the National Academy. So I'll start with what the structure is going to be. So I don't forget people. I will not have everyone on the slide, but at least credit my colleagues. And then we'll talk a little bit about the sort of theoretical context, model reduction dynamics, how it can be used, how we've extended the methods of reductions we had, and then this really exciting conclusion that we might be heading towards a new general theory of how to model locomotion that would be very useful for the class of robots that I've been working on and that have hitherto sort of not been used much, in part because no one knew how to control them. So thanks. The faculty who have worked with me on this are primarily Professor Ross Hatton, who taught me a great deal about geometric mechanics, and Nick Gravish and Glenna, who did the ant work in the paper I'm going to show you, and also asked me all the questions that help crystallize my thinking about this. Some of my former grad students who have graduated, some people who might be in the room, and other students who have contributed to this work. So first, I'm going to ask you a question, right? There's this thing called dynamics, how things move in the world, and those can be really complicated. So we want to be able to reduce our models. We want to have simpler models. And very broadly, I'm going to say there are two important methods out there. So if we look at dynamical models, and here, unsurprisingly, I'm showing cockroaches because that's what I worked on as a biologist. So this is a very detailed model of a cockroach. Someone actually took this cockroach and sliced it and put the slices in a CAD program and then modeled it with atoms to see how it moves. That's a very detailed model. This model on the other end is really abstracted. It's just a spring and a mass. But all of these are models of various detail. And this idea was actually of using these different levels of details and models is encompassed in the notion of what are called templates and anchors. Those more abstract models are templates with respect to the more detailed anchored models. There's a good but somewhat old review on locomotion regarding that, but there's also something a bit newer. And if you're interested in more context on how people think about this, there's a book on bi-inspired legged locomotion, which has also a bunch of interesting stuff about control of legged robots, and we contributed a couple of chapters too. So this is sort of the framework in which my work sits. And now there are two really fundamentally important notions of dimensionality reductions. One is what's called a phase reduction. So the idea of a phase reduction is that the template, the simpler model, is actually a submanifold embedded in the state space of the anchor. Here, the template is this sort of oblong shape you see here. And the ambient dynamics are these arrows, and you see that states collapse onto the template, and then they evolve on the template with the template dynamics. Algebraically, it expresses itself through what's called a semi-conjugacy. So the flow of the system doesn't care if you project to the template later or first projected to the template and then took the flow. That is, I could go out here and then project down, or I could go down, or I could project down and go here, and I'll end up in the same place. Okay. So it really means this is a simplified version of the model. Everything the projection threw away, we didn't need to look at for the long-term dynamics. And the most common form of phase projection is projection onto a cycle, onto an oscillation. This is why people usually think of phase as just an angle. because most of the time the phase models we have are oscillations. And so, of course, the first thing I wanted to do studying cockroaches is a cockroach an oscillator? So this is a density plot of the state of a cockroach measured from a whole bunch of variables. I think this is about 24 dimensions, but projected as a density on the first 3 principal component. And what do you see? Well, you see a donut, right? And what you don't see, I don't show you the time flow here, but as the cockroach is running, it's cycling through this donut. So you have this big complicated system, 24 dimensions. You'd never be able to write the equations of motion. But inside, it's just a clock cycling on a circle. That's the beauty of phase reduction, is we can sometimes throw away a whole lot of complexity and get to a really simple model. The other kind of important reduction you see in dynamics is what's called symmetry reduction. And that has to do with the fact that although each of us thinks we're special, the laws of physics don't agree. The laws of physics don't depend on who's watching and what the frame of reference is. And so you can always rewrite the physics of a system in terms of how the frame is changing and what the shape is relative to that frame when you're talking about a locomoting system. So I'm moving around. What is the shape of my body? It's the part of my configuration that you could imagine translating over here, and it would be the same in some sense. Okay, so there's a symmetry group, the symmetry of rigid body motions, that we can factor out of the dynamics. And that's this idea where you can commonly write equations of motion in body coordinates. It basically reduces the equations by the dimension of the symmetry. So the more symmetry we have, the more things we can say, okay, we know how these relate to each other, the simpler the equations become. And if you take that to its limit, which some folks have done in the 90s, one of whom is here in Michigan, Tony Block, this idea of geometric mechanics and what's called the Reconstruction Equation. So they can show that if you have a system that's symmetric under some group, you can always rewrite the dynamics in this form. This is the body velocity. So G here is the group element, rigid body group of the body. G inverse G dot is the body velocity. It's some function of nonlinear function of shape times rate of shape change, plus what's called the fixed inertia tensor. It doesn't matter what this tensor is, but a momentum. But this momentum is not the momentum you might have learned in Hamiltonian mechanics. This is a momentum that is a group momentum. Its dimension is the dimension of the group. So this is the momentum of the center of mass. So this is pretty weird when you think about it, because where did all the forces disappear, right? I know how the body moves, but I had a really complicated body with lots of internal forces that could have done really complicated things. They're all gone. All that's left is this momentum. And that's what's so cool about it. Okay, the symmetry reduction, especially when the momentum falls away, which is what I'm going to talk about next, throws away a lot of complexity and relates velocities to velocities without the need of force as an intermediary. And when does this become important? Primarily in motions that are dominated by friction, where this momentum term dies away quickly. So if I'm moving in a regime where the moment I stop reshaping my body, I glide to a standstill very quickly, I don't build up momentum, this term is gone. We don't need forces at all. It's an entirely geometric motion. And so the way to conclude, what you can conclude from that equation is, if you can control and measure the shape of your own body, your dynamics are actually at most 6-dimensional. Now that's where we actually are in robotics. We have high gain control of the shape of our robots usually. So we can control the shape, which means that potentially using this idea of symmetry reduction, we can get a lot of mileage. And indeed we did, and I'll show you some of the things we've done with it. So, but before that, I want to sort of map where this is in the grander scheme of movement. So let's first talk about where that reconstruction equation, which is this kind of movement, lives in the land of different kinds of movement. The simplest kind of movement is actually holonomic. That's what you get from robot arms. There's a map between the shape and the location of the center of mass. If I plant my leg, it's now can't move from the ground, and I move around, you don't actually need to know anything about dynamics to know where my center of mass is. You just need to know the shape of my body. Because my foot is planted, that's it. You can just solve the structure. Okay. The problem is I can't move. Why can't I move? Because if my shape comes back to the same shape, my center of mass came back to the same center of mass. Right? It's an actual function. It has the same input. It's going to have the same output. But the next thing you can do is what we humans do when we walk. It's piecewise holonomic system. While my left foot is planted, I can do that calculation. Then I plant my right foot and I can do the calculation again. But now I'm back to the same shape and my center of mass has moved. So as soon as you become piecewise holonomic, you can start having motion. But it turns out that if you look at the structure of that equation, body velocity is some shape-dependent matrix times shape velocity. That can happen even if that matrix there didn't come from being the Jacobian of any function. And that's what happens in friction-dominated regimes. There is no function for which that connection, as it's called, is a derivative, but that function still exists, that AFR. And you get a lot of structure that you can learn about how a system moves. And as we've shown in our own work and is related to other papers that predate us, if momentum is still there but decays quickly, that relationship still kind of exists. Instead of being a perfectly linear relationship, it starts deforming a little. But there still is a function that relates R and R dot to VB, rather than requiring the additional momentum state. And eventually, there's so little friction that momentum starts being important. And for different values of the momentum, you'll have a completely different relationship. Okay, so for the most part, people haven't studied these motions that live in the middle. And that's what we've done in the last few years that has led to some interesting results. So the obvious thing to do is, well, maybe we can measure the connection. My colleague Ross Hatton with a bunch of physicists actually tried to measure the connection for a really simple system. This is a 3-segment robot in a bucket of beads. It just wiggles around. It tries all the different positions because there are only 2 degrees of freedom. That's not too big a space to try all the positions and all the velocities. So for 2 degrees of freedom, 4-dimensional space being sampled. Okay. Measure the connection, compute what it is, try and maybe find a better way to move, a more efficient way to move. But then I met Ross at a conference and we came up with this idea. Well, it's kind of hard to sample the entire space when you have more degrees of freedom. You know, sampling a 4-dimensional space is painful. Sampling a 6-dimensional space is excruciating, and anything beyond that is just practically impossible. But if we do have the ability to reconstruct the phase of an oscillatory behavior, then all our behavior exists within a thin tube in the state space. And thin means that going across the tube, our changes are small. And so we could expand those in a series expansion. And along the tube, we still maintain all the nonlinearities that existed before. And this becomes a bigger and bigger win as the dimension goes up, because we're basically sampling a 1-dimensional space no matter what the ambient dimension is. Okay, so we tried to do that. And here's why this is really good, because we often don't know the physics of the robots we work on, or the animals. The robots break. And if we try and study gaits, which are basically these trajectories in the configuration space of the robot shape space, those are very high dimensional objects. So if we tried to study things exhaustively, we would be in a lot of trouble. But if we can get a good local model of the physics, a local model within that tube, we can simulate how changes of the gait would work against the model. Now we're not doing a robot experiment. We won't break our robot. And we can optimize whatever we want to optimize in the behavior of the robot and keep doing this until we have a good gait with a good model. And then we have a working robot and the ability to control it because we have a model. Okay. But there's something else even more exciting. So this is sort of weird, but when you simulate Newtonian mechanics, how many computation steps do you need? Well, the state in the future depends on the state in the past, right? There's a dependency that's carried through by the momentum. And so these dependencies mean that if I want to compute for a time horizon t, I need to do something linear in t in terms of computation steps, even on a highly parallel machine. But because our connection model, VB, depended on something that was purely a function of shape, there was no history there, and I am controlling shape, I can control the VB contributions in advance. And so I can do all these computations in parallel and then combine them in logarithmic time. And so this has the potential of allowing us to compute fairly long horizons into the future on parallel architectures very, very quickly. And so it's not only sort of mathematical convenience, there's also a real paradigm shift in terms of the computational complexity of planning for this class of systems. So how do we do this magic? Well, we try and build, somehow this is displaying a bit off, so I'm sorry that my Greek letters have drifted from their appropriate locations. So let's say we have some data of the system moving in cyclic fashion. We bundle the data into groups of equivalent phase, and those are represented by theta. Theta is the parameter in state space that's going around the cycle predictably the same way every time, but every instance of this cycle is slightly different, and that's captured by delta. The beauty of delta is small. And because delta is small, I can take this equation here, which is what I'm trying to model, partition it, and then do a first order approximation. This is just Taylor series. This is nothing fancy at all. I do the Taylor series, I multiply everything out, I end up with a linear regression. And it's not a terrible linear regression to do. I do this in each of these segments, and now I have a physics model that's computed entirely from the data. Okay, I basically learned the physics of my robot by observing. Why do I think this is going to work well? Well, because how many samples does this linear regression need? At most, on the order of the dimension squared, at most. So that's the number of cycles I would need to see. So if I have a 26-dimensional robot, that starts being painful. But the reality is we've often seen that these terms are very small, and then we end up with even the linear number being enough. But let me show you some results. But before I show you these results, I'll say, this is really naive, right? This is Taylor expansion. I'm modeling a complicated nonlinear system with Taylor expansion. You ask, okay, why don't you use more sophisticated machine learning techniques? We've now started trying to do that. I have only preliminary results with a student who's been trying to use SVR-based regression. Sometimes it works really well. This is about as well as our linear phase-dependent model. Sometimes it gives us really weird results. So, you know, that's all I can say right now. This might work well once we finish tuning it, or it might be no better than the phase-dependent model. But here's sort of what happens. So here's a simulation of a wiggling thing in high viscosity fluid. It has a lot of segments. The dimension of the gait here is about 264, so it's a large optimization. A lot of parameters need to be learned. It's doing a bunch of cycles, building a local model, improving the gait a little, rinsing and repeating. And you'll see that each time it moves across, it does about 30 cycles of swimming. So this is not something huge. This is not the sort of data sets you have for machine learning where you want 10,000, 100,000, 1 million cycles of motion, right? This is only a few tens of cycles. And after 10 iterations here, I don't think I'll let this run to its end, but after 10 iterations here, you have a pretty nice wiggling swim that looks very natural. So it's basically finished optimizing the gait and found something that we knew it would find, because this is how animals swim under these circumstances. So we compared optimizations under a lot of conditions, and I'll just get you to the conclusion. This is a very robust method. It's robust under choice of initial conditions. It's robust to the level of noise, even very aggressive levels of noise, where you see the noise here is on the order of a third of the diameter of the cycle. So imagine I'm taking a half-meter step and I'm off by 15 centimeters every step. That's a pretty aggressively noisy system, and this optimization still works. So then we tried it on a real robot. So this is a robot learning how to move completely from scratch. So this was its initial motion. As you saw, wiggling one segment, that's all it knew how to do. Now, the main thing I want to tell you is you're seeing all the data. Okay, this is not us cherry picking just the parts that were important. This is the entire optimization. Okay, this took 15 minutes. The only part you didn't see is the student picking up the robot and moving it back to the left side. That's it. So much faster than other learning methods we've seen in robotics. Okay, and this is a pretty high dimensional thing. This is a 5-segment robot. So seems to be a fairly powerful method. So then we tried extending it. We did a whole bunch of extensions. One is, well, what happens when there is a little bit of momentum? It turns out you need a few extra terms in the expansion. And when you add those terms in intermediate Reynolds numbers, in intermediate cases where there is a little bit of momentum, not a lot, not so little that it just doesn't matter, but in the intermediate cases, you get a big improvement in accuracy. And to show you sort of what that looks like, the simulated motion is in red. If you don't add the extra terms is in blue, and in green is what you get if you add the extra terms, and does a pretty good job, right? So the motion in green, data driven, doesn't know anything about the physics, just sees the motions, recovers them. Okay. And we've also realized that this will work in the case where you have only a few active motors and everything else is passive. So in this case, for example, we have this whole snake that have only 2 motors wiggling at one end and everything else is flopping around passively. We get about 90% recovery in terms of accuracy of the body velocity. And we've also looked at, I'll skip a little bit. We've also looked at the idea of how do we create libraries of motions in an efficient way. So if we can optimize motions very efficiently, maybe we want to have a really expressive library of motions that will allow a robot to navigate through its environment very efficiently, but now without making any a priori assumptions about how it should move. Just find me a library of 3 motions that lets you move as effectively as possible. And so we do that, and it works really well. But then we did something interesting, which is we broke the robot and let it try and learn how to recover. And what we found is one of the very few times I've seen this in learning literature where the more complicated robots do better. Okay, it's easier to learn how to recover when your robot is complicated and has more degrees of freedom to exploit, which is sort of our experience as humans, right? If you can just move one joint and that joint is stuck, you're in trouble. If you only have a few motions you can do, but the more you can sort of wiggle, the more things you put into play, the easier it is to get out of a tough spot. This seems to have the same qualitative behavior. So just to quickly illustrate what that looks like, here we're learning a family of maneuvers. So we learned 3 maneuvers. We're trying to optimize them so that we can get to lots and lots of different places. And you see how these worms are sort of covering the space. Now we broke them. They're having trouble moving around, and they're learning how to cover the space again very, very quickly. And so again, we went and tried to do this, demonstrate this ability also on a physical robot. And this is in part, Brian got a bit annoyed at people constantly thinking that he has models for his robots. So he just went outside one day and grabbed some sticks and strapped them on the robot. So there are no models. And the robot learns a family of maneuvers that allows it to navigate on the plane in about 20 minutes. So a very, very powerful learning paradigm. So that got us excited to try and think, is this more general than we thought? And so what we did was talk to some colleagues about getting data from animals and other systems and look at that. And so we're trying to focus on basically these motions. It's either piecewise holonomic motions is what you get when you have a legged system moving around without slipping. So the foot is planted in the ground and it's just switching. It could have Stokesian motion like in viscous swimming, or it could even have a little bit of slipping. What's really going on here? Are these good models for legged systems? And basically the next segment of this talk will be me walking you through this paper that just came out 2 weeks ago in Proceedings of the National Academy, where we talk about this. So let's talk about some animals and robots. So we've looked at ants, we've looked at cockroaches, even though they're not in detail in the paper. We've looked at 2 of our robot families here in the lab. Ants slip almost none at all. Okay, so these dots here are where the legs are on the ground. And you see that the legs are on the ground, they're not moving much. Cockroaches slip a bit more. They have a little bit of slip. This is a moderate speed. This robot doing this turn is doing some slipping. This robot is doing a lot of slipping. Now, people have generally thought, and this is true of humans, but not of these robots, as it turns out, that if you slip, you have to be dynamic. You have to think about forces and momentum. Turns out that's not the case at all, and I hope I'll convince you of that. So just a quick look. These guys built an amazing system that auto-tracks millions and millions of cycles of motion of these ants for a whole bunch of interesting biological and biomechanical questions. We helped them some with data imputation to sort of improve the conditioning of the data, but part of this is based on some machine vision, and so we're talking about 2 million frames of ants walking around. Okay, so lots and lots of data. And so one thing we expect is if the motion is geometric, what's going to happen is the body has the same set of shapes at all speeds because it's not being deformed by its inertia. There are no inertial forces deforming it. And so the animals moving slower, moving faster, you have the same shape. So we partitioned our data into 4 categories of speed: lower quartile and then 3 more quartiles. We threw away the low quartile because when the animals are slow, they do all sorts of other behaviors, not just walking. And now we're comparing animals, and then looked at animals turning right, turning left, or walking mostly forward each cycle. And here we're looking at just 2 bins, the animals going quickly and the animals going slowly. So 3rd and 4th quartile forward motion, basically indistinguishable. Red and blue, the same distribution of leg motions. So check, that looks geometric. Now, one would hope that the speeds are actually different because the animals are walking at substantially different speeds. If you look at the speeds, you see they are different, right? These red lines and blue lines diverge in various places. So the animals are actually walking at a different speed. They're just doing that like clockwork toys, following the same tracks for all their limbs, just doing that at a different speed. Well, let's do another little sanity check on the data. It should be the case that if I take ants rotating left and I reflect them in a mirror, they look like ants rotating right. Otherwise, something's going to be very weird given that ants are basically bilaterally symmetric. Turns out that's pretty well correct as well. So we have some sanity checks. This looks like a reasonable data set that is describing what they're doing. So now let's try and do the following. Let's build a model from ants walking at moderate speed forward and see how well it predicts motion in all the other conditions. Okay, so we're learning here, and then we're extrapolating out here. And there are 2 ways we're thinking of learning. One is just what is their typical cycle? Are they doing exactly the same shape? 2 is, well, that's a bit unfair when you're changing speed, because one would expect that on average, your speeds are higher then all your motions will be faster. So we just take the typical cycle motion and we rescale it to the average speed of the animals. And the last box, the colored box, is what you get from the geometric mechanics model. And what you see is obviously you don't have very good prediction when you change speed, but don't account for it in your geometry. But if you do account for it, you get a 14% prediction, which is what we get with our fancy models. So this might be a complete waste of time, right? Well, not quite, because if we look at turning, there's a huge difference. So we only looked at animals walking straight forward. We didn't try to predict how much they turn. So this is trying to predict their forward speed, but now we're trying to predict their angular speed. How fast are they turning? We trained only with animals who are walking mostly straight. So there isn't a lot of turning in the data. But it turns out that we learned the physics so well that we can predict 50% of the turning velocity with our model. So we did actually capture something in the physics there. Okay. So what we're seeing is that the data-driven models, based on these assumptions, are actually giving us pretty good prediction of the animals. You guys might not be used to animal data. 55% prediction on an animal is spectacular. It's not what you want for your rocket, I'm sure, but for anticipating what an ant does, that's pretty good. So we tried one of our robots that has a rigid structure. Oh, I'm sorry. So this robot is walking on an arc. We studied a whole bunch of things related to steering and slipping. So this is data that was collected for another paper. But the important thing to see is that the legs are slipping a lot. Okay, so if you believe that slipping has to be governed by momentum, you'd think, okay, this connection-based model that ignores momentum can't possibly be true. Let me point out that the robots are doing exactly the same motions at all speeds and at all turning angles that we've used. So they're really rigid enough so that they're basically going like clockwork toys through the same shapes. But they are doing different turning arcs at different speeds. So we change speed all the way from 0.10 hertz to 0.34 hertz. So a factor of 3.5 in speed. And we changed the parameters that govern the turn to change the turn angle quite a bit. Okay, so we're actually exploring a whole different, a variety of different behaviors. One interesting thing we're seeing is if we look at how much response we get for our turning behavior, so how fast are we turning for different speeds, it looks like the response is independent of speed, which is what you expect from the geometric mechanics equation that had no velocity, no time dimensions in it, right? Time didn't appear anywhere in that equation. So how fast you did things shouldn't matter to how fast you traveled or how far you turned. And that's what we kind of see. There's basically no slope. So that's beginning to suggest that they are governed by geometric mechanics. So let's see if we can predict how fast the robot moves. The other model is doing pretty poorly. We're at, by the way, this is just 100%. So that's why the numbers aren't in here. So this is 70, 80% prediction. So pretty good prediction for speed, pretty good prediction for turning, all on training data of the robots walking at the intermediate arc. So this is, we had those 3 bundles of lines. That's taking data only from the middle bundle and extrapolating to the other bundles. Okay. So we actually can learn a lot about this robot's physics using this very, very naive method. So you say, okay, we need more slipping. This is just too rigid. Let's do something that has lots of slipping. So we had another family of robots we built. These robots slip a lot. This is how much they slip. Okay, so you see most of their motion on the ground is kind of sliding. And we have them at various sizes from 4 legs all the way up to 12 legs. going at a whole bunch of different speeds at a whole bunch of different phase offsets. Again, data that was collected for another paper. But what we find is that if we want to look at distance per cycle, how much they travel, it turns out that it only depends on the phase offset between the legs, not on the number of legs, and not on the speed. So it's like all of these are sort of clockwork toys moving through the same motions, even though these legs flex, right? These are not rigid legs anymore. Until we get the very highest speeds where the deformations start being significant. So what you're seeing here is we collected this master curve, and then we ask how much do we need to correct that when the speed gets higher. It turns out only at the very highest speed. So this is 10 times as fast as the slowest speed, we start seeing a change. How much do the number of legs matter? Almost not at all. So you'd think that a 6-legged robot and a 12-legged robot walking a factor of 10 in terms of speed different from each other would behave differently. It turns out that the 12-legged robot is like 2 6-legged robots walking in a convoy, and you don't even need to know how fast they're moving. So it's vastly simplifying what's going on. Okay. So I'll skip this as well and say the next thing we wanted to do is, okay, this looks really promising. Let's try and simulate this. So my student Dan tried to write a simple model where you imagine the robot has a bunch of spring legs that have friction on the ground. And there's sort of a little problem with that model, which is that to get a connection type model, to get this linear relationship between input velocity and output velocity, you need homogeneous constraints. You need the mathematical structure that just isn't there because Coulomb friction doesn't behave that way. The kind of friction that you have dry on dry contact that you learned in high school physics just doesn't have the right behavior for this. So we did what physicists sometimes do and use an ansatz. We just said, heck, we're just going to bludgeon the math into shape. We're just going to change the little hat on V. Instead of the force being proportional only dependent only on the direction of the contact velocity, we'll also make it scale linearly with the contact velocity, and everything works fine then. You get nice equations, and those equations have a closed form solution, and we tried the solution, and we compare, this is green and blue on that robot and on this robot, and it was annoyingly good. This is terrifyingly accurate compared to what we would have thought. And so we asked colleagues for data from their robot, which has 4 legs. So it's not even in real high friction contact with the ground, it's wobbling. And even there, it worked pretty well. So now we knew we were in trouble, because when you have a model that's working too well, that has the wrong physics, right? We bludgeoned the physics. This is the wrong friction. And it's giving us the right result. How right? 0.9293 R squared. So very, very good fit to the data. We need to understand what's going on. It took us a long while. One reason it's working is it turns out that if you try and ask when I'm sliding at some fixed velocity, let's call that velocity 1, and I'm undergoing Coulomb friction, there's going to be a force backwards. I could imagine that I could also be trying to generate the same forces using some viscous friction. What's the difference between the nearest viscous friction model and the Coulomb friction model? Turns out, thanks to what my student Yo-Yo calculated here, it's actually really small. So this is a relative error. It goes up to 2%, while the velocity changes by 20%. So it turns out that if you're sliding under Coulomb friction, that's very, very similar to moving under viscous friction. So similar that the errors are pretty small. I also had another student work on now that we have a computational model that works so well on parallelizing things on the GPU, and I will just point out this quick thing. can easily get speeds up of over x300 on a GPU doing this. So this promise of parallel computation of these models is good. But now, how do we solve these models? So we have multiple legs. They need to contact the ground. How do we solve the contact problem? That can be really tricky if your robot can tilt and move. Well, here's an intuition for how we do this. So imagine I have just a 2D robot. I have a robot with a bunch of legs and it's dropping down on the ground. I have a pitch angle parameter and I have a height. So I have two parameters here. Well, each leg is going to be on the ground with regards to these parameters when it's below a certain line and off the ground when it's above a certain line. The slope is dependent on how far the leg is out, because that tells us how much pitch is going to matter. And the offset is related to the leg length and z. So I just drop the robot down on the ground until one leg contacts. So once that one leg contacts, I can solve the equations and it projects a solution here. But it turns out that if I try to move to that solution, I'm going to hit a line, which is another leg is going to hit the ground. Well, the motion from here to here is a simple projection operation on this plane. Now I can do the same here. I calculate the solution here, and it turns out it's out here. I project on this plane, which is the next plane I hit. And so this very quick process of projecting until we hit a solution, much, much faster than a conventional mechanics simulation. We can solve which contacts are on the ground and then use our connection model. The 3D version is kind of the same, except you have now two angles. You have a pitch slope and a roll slope. And so it's a 3D thing instead of a 2D thing, but it works. Okay, so we have a quick way of computing a pitch and roll, finding which legs are in contact with the ground, computing their forces in force balance, and solving our connection model. Now we want to justify that model. So we had really accurate results from the wrong friction. There are two ways that could happen. Either somehow the right friction generates something that looks a lot like the linear viscosity that we forced it to do, even though it's the wrong physics. Maybe the answers are just the same, or maybe the friction model is wrong. Maybe the way the legs interact with the ground effectively generates a different kind of friction model than what we thought. How would we separate out these two hypotheses? Well, unfortunately, the only way you can do that is by knowing what the forces are on the legs. And it turns out no one measured that. So simultaneously measuring forces on multiple legs of a multi-legged robot, turns out no one's done that very thoroughly. So we're lucky enough to get a nice grant from the Army Research Office to build a robot to look at that. And so this was built by a few students. It has these pretty fancy force torque sensors at the base of each of the legs. So this is actually the most expensive robot I ever built, even though it's built primarily out of foam core, because it has about $50,000 worth of sensors on it. And it sort of moves like this. Then we give it gaits that are designed to make the legs slip a lot. So we really want to see, is this slipping governed by the physics we thought it should be governed by? Okay. Now, it turns out it's really hard to calibrate out this robot. My poor grad students spent a year and a half getting the force measurements to work, because we have our force transducers here. There's a leg outside that. That leg is going to generate a different error with respect to the ground contact force with every different position the leg could be in. So that needs to be calibrated out. That looks like this. So as a function of phase, you have some cyclic dependence of that. But it turns out the force calibration of these sensors is not that great either. So what you see here in the sort of warm pastels are the before calibration results for our sensors. And in places where we're talking about, say, lateral force, Fy side to side, we'd expect the force to be 0. It's really not 0. Okay. When we tried to combine all these sensors together, we got pretty bad results. And it took a lot of work to calibrate. I'm not going to get into how that was done, but I will say we eventually did calibrate it. And so you see we go from here to this teal line, which is on 0 where we expect it to be. So we now have a reasonably reliable measurement of force. The situation was even more tragically bad with torques, because torques are even trickier to measure. The torques are also calibrated reasonably well now. And so now we can look at how our model prediction of forces, which are not even important because the model predicted motions without knowing the forces, but how our model prediction of forces compares to the measurement. And this is a slightly modified model from the one I described, but it sort of should give you the idea. And what you see is red is our experimental data. Purple is what you would get if you did the actual Coulomb friction. And blue is what you get if you use our linearized friction, which can, the equations can be solved much, much, much faster. There's basically almost no difference between Coulomb friction and our model, even though we're using completely the wrong physics. And we're getting a pretty good prediction of the forces. We're getting a pretty good prediction of velocity in the direction of motion and of turning. Side-to-side velocity, which averages kind of to 0 on this gait because the robot is moving a lot, not predicted quite as well in terms of relative error here. But this is a pretty good model. And so what did we find out from this? This Stokesian connection kind of model of the physics of multi-legged motion is actually easy to learn from the data. We can collect data, we can learn it. These models applied to most friction-dominated motion. They apply to little worms swimming in the mud. They apply to big robots that slide on the ground with a lot of friction and have legs. So domains that we thought were completely unrelated to each other are actually all governed by this. It seems that the only thing you need to know is that your system is governed by a lot of friction. And computationally, they have a lot of advantages. And this makes me very excited because I've been working on multi-legged robots my entire career. I started looking at cockroaches in part because of the interest in multi-legged systems. And we're finally in a place where we might be able to do real motion planning on these systems, where before people didn't want to touch them because this multi-contact dynamics. How does the load trade off between the legs? Simulating which leg hits when. All of this was really slow and cumbersome to do with conventional simulation tools. And what we're finding out is we just don't need those conventional simulation tools. In fact, we can use a completely different mathematical formalism, get pretty good prediction, and also compute in log t our time horizon. So the potential to do planning and model predictive control with these systems is huge. And so I hope that's what you'll see me doing in the next few years. Thank you. So, any questions? If there are no more questions, I'm happy to go. Yeah.
Have you tried looking at sort of learning the model as it's walking and sort of like an adaptive?
Making it adaptive?
Yeah.
This is a great question, and this is in my next grant proposal. Yeah. So there's a very natural way to do this, right? Because we're doing a linear regression,
Yeah.
and converting a linear regression to an online update, you do rank 1 matrix updates, it should work. Yeah, yeah, begs to be done. And what I hope that will do is it will have us have a robot where it can go on, say, hard ground and move on to soft ground and just adapt its model and not lose any predictive power. Yeah. Other questions? Yeah.
Quick one. So the way I understand what is happening here is a little bit of an evolution in the robotics first. So people design some robots, and then there is this investigation which is trying to figure out, what is the low dimensional subspace where they are moving and kind of really understanding the motion.
Mm-hmm.
But if there is really a low dimensional subspace, can it be kind of like flipped around and say, well, based on this, this is the essence of this motion. I can actually change the robot design. So kind of like, rather than in a trial and error and figuring out.
Yeah. So I mean, the work I did here was not trying to find a low dimensional representation, but really trying to get at understanding the physics, whether we're using the right physics to represent these systems. But if you go and look at this book, which I mentioned in the initial slides, it actually has an entire chapter dedicated to basically this idea of how do we use templates for control, and sort of how can we take an abstract low dimensional idea of how the robot would move and then instantiate it in a body. So yeah, people have looked at that. It's a fruitful direction. Yeah. Other questions? Yeah.
You mentioned that you were trying to use a support vector regression instead of a linear model. Why is that model being tried instead of others?
Oh, I'm happy to try whatever machine learning method of choice you want, right? But
the question was there something specific to that model? Because support vector regressions that has some characteristics that other models do not have. Especially in learning, there are some that model satisfies some generalization constraints that other models do not satisfy.
Yeah, so there isn't a strong machine learning motivation for why use SVR versus something else. I think the main motivation is that we know our training data is laid out in a certain way geometrically in the state space. And SVR seems like it could deal with that better than other approaches we try, but we're planning to try other approaches. SVR was the first thing we tried that wasn't just linear regression. Yeah.
So your viscous model matched nicely, with the cool model, but does that consistent across like the material that the robot is walking on?
So that's a great question. How does this change with material properties? So I'll say a couple of things about this. First, we have data on rubber mats and on floor, and we kind of get the same results. But beyond that, if you actually look at the structure of the equations we get for this model, so let me pull these guys up. That's as much of the equation. So I don't show you the friction equations here, but it turns out that when you solve these equations, they actually co-vary with the scaling of mu. So if all the friction coefficients increase by the same multiplier, the result remains unchanged. And so that means that at least to some extent, the system is invariant to the surface. It depends. The only thing that changes is the magnitude of friction. As you switch from surface to surface, you'll get the same answer. You only get weird things when some of the legs are on one surface and some are on another. And there's more interesting to say there. It actually turns out that if you do perfectly inertial motion, so let's say I figured out a way to move my legs so that my center of mass is moving constant velocity, okay? Then I could do the same motion at different speeds and it would still work. You can show that basically the solution becomes time rescaling invariant under those conditions, as long as all the legs have the same kind of friction. So if all my legs are on Coulomb friction, it will work. If all my legs are in viscous friction, it will work. If all my legs are in dynamic Coulomb slipping, it will work. It's just when some legs are doing one thing and some legs are doing another that it won't work. So this is actually pretty robust to changes in the kind of friction, is the short answer. Yeah, other questions? Yeah.
This is kind of ties into the last question maybe, but I think you showed a lot of, examples of the robustness, but were there any like certain failure modes that you found interesting that you maybe learned something about?
So failure modes of the modeling, failure modes of the robots, what?
In either, like the learning procedure, like I wasn't able to, pass this on.
That's a good question. Maybe I will go back to this slide, which I didn't show. I sort of skipped through it, but so we have these robots, 6 to 12 legs at 5 speeds. As it turns out, if you rescale the velocity of the robots to the frequency, so you divide velocity by frequency, if the motion is perfectly geometric, you should get the lines overlapping. That isn't what happens. It turns out that at the lower two speeds, they kind of overlap. At the higher two speeds, they kind of overlap. And in the middle speed, they're doing something completely different from the other two speeds. So that was one case where we sort of failed in our prediction. I would put that in quotes because this robot has a lot of elasticity. And right, this is a really bouncy robot. And so what I think happened there is we switched between one sort of resonance regime to another resonance regime. And so the shape of the motions changed. So this theory works great if you can control the shape. If your shape is dynamically emergent through interactions with the environment, then it will only work to the extent that you know what the shape is. But what this tells you is you can learn how to move by knowing your shape rather than by needing to control your shape. It also tells you that. That is, if you can measure the shape, you can build a model, even if you don't have strong control authority over the shape. Yeah. Any more questions? Okay, thank you for listening and for these interesting questions.
Thank you. Try to scale it down. Sorry, I wasn't able to come earlier, but I was listening to it from my car. So
No, thank you for coming. Well, I mean, there'll be a recording, so you can see the videos and all those things. Yeah.
I feel that if I don't watch something in real time, it's really hard to kind of go back.
To build the motivation.
Yes, right. I thought I really enjoyed it. Basically went back to PhD essentially, right?
Oh, 我还以为是在 contact point 上面，我也是在想，好有意思，谢谢，好厉害。那个 innate transform 是上过课的人。
他现在在教那个
really need to understand.
就是说，他最开始讲那个 dynamic， 就是 dynamic 那个什么意思？就是说，就是第一个就是那个叫什么 low dimension
Dynamic equivalent friction is actually very simple.
第一个那个就是它显示出动量 position，
When you think about it, you change your velocity sideways.
就是没有 force， 就是
没有
他的意思是说，就是没有 dynamic， 所以就是你人想怎么动怎么动，是这意思。
So what happens is
就是纯 geometric 的想怎么动。
linear approximation still works, which is just not the way I think anyone thought about it.
No.
It's here's what you're seeing.
练了5个那个就是 motion， 就是五种 motion，
Something very nonlinear, right? It's concluded nonlinearity.
然后那个